All right. So let's see. When we left off at sorting, right? And we left off at insertion sort, yes? So insertion sort isn't too, actually, for what I'm doing here, I don't really need any of these. And also, I finally found my hidden stash of all the markers I ordered. And hopefully that some of them are still good after I've used them for a while. So, yeah, decent at least. All right. So we went over insertion sort, which I said was superior to the other O of n squared sorts because it's very efficient. You get a lot of stuff for free while doing it, and it's and by a lot of stuff, and it's online. Meaning you can do a bit of work, and then you can take a bunch of other items and then insert them in place, right? Insertion sort, if you've got an array, 1, 2, 3, 4, 5, 6, 7. Actually, let's put this 7 here and then 8 over here, right? Right. You start out with a sorted portion, an unsorted portion. We push 4 into the sorted portion. It doesn't need to go anywhere. We swap 1 with 4. We swap 1 with 2. No problems there. To put 7 in, we don't need to put it in anywhere because that just simply gets added to the sorted portion. To insert 5 into the sorted portion, we swap it with 7, but since 5 is bigger than 4, we don't need to insert it anymore. So now here's our sorted portion, our unsorted portion. We add 8 to our unsorted portion. Sorry, to the sorted portion. We don't really need to do anything there. That's what I mean when we say we get a lot of items for free. They just kind of get inserted automatically like that. 3. Right, we're going to have to swap 3 with 8, 3 with 7, 3 with 5, 3 with 4, and put 3 here. And then 6 has to swap with 8 and 7. It doesn't actually take all that long. In fact, a lot of times, it works pretty well for anything that's up to 64 items. So well, in fact, that algorithms like Quicksort and MergeSort will sometimes just default. They'll say, oh, if there's 64 or less items to sort in this array or subarray, we're just gonna insertion sort this bit because that's just quick and it's not really going to add to our runtime because if it's less than 64, we can pretty much count the amount of time it's going to take. More as a constant than anything, right? Now, let's see. So now we've got, so we've learned insertion sort. So now it's time to learn about the O of n squared. Sorry, so these were the O of n squared algorithms. Now insertion sort, of course, also does really well in our worst case scenario. Does anybody remember what from last week, which is like forever ago, right? What the worst case scenario for sorting was? Sorry, not our worst case scenario. It works pretty well in our best case scenario. What's the best case scenario for sorting? Sorry? You don't have to move anything, or maybe just one thing. Maybe one thing or nothing. Maybe one thing's out of place or nothing's out of place, right? If it's already sorted, then ideally for a sorting algorithm, there's no work to do. And so you can see with insertion sort, you're just simply adding each item to the sorted array because it's already sorted, so there's no need to swap with anything, right? So that makes it pretty nice. Screen protector. And so insertion sort is really nice because the best case runtime is O of n. Worst case scenario is O of n squared. What about things that are faster? There are things that are faster. And we're going to learn about we're going to learn basically we're going to learn all about them. Really? There's so many slides here. All right. So one thing that I'm not going to go over too much is Shellsort. I'm just going to briefly mention it because if you're interested in getting into research and you're saying, well, sorting looks interesting, but I'd never really think I could get into it. It's a dead field, right? Because it must have already all been solved. That's where you're dead wrong. Shellsort is a better version of insertion sort. It's not named after the fact that it like creates shells or anything. It's named after Donald Shell. And essentially, it gives you, instead of getting O of n squared, we can get O of 3 over 2, or n root n, right? Rather than n log n or anything, this is n root n, which is pretty small, actually. So, and what it does is essentially it like creates, it sorts small subsections of the array, and just creates smaller. It starts out with a gap sequence and then it creates smaller and smaller gaps and just insertion sorts like small sections of the array. Like it will insertion sorts this subarray, then this subarray, then this subarray, then this subarray gets insertion sorted. Then this, and what that does is that once we do this pass enough times, we do a single run of insertion sort, but because of the way everything's already been kind of pre-inserted sorted for us, we don't actually have to push items down that far at all. They just kind of, like 70 gets swapped with 75, 75's there, 90 doesn't really have to do anything, we swap once, right? We end up swapping like only once or twice for each item, which makes it run really fast. Now, we don't know how, the reason I'm not going to go into this too much is because I want to get into the more stuff that's going to show up on your exam. Not really teaching to the test there. I'm sorry, teaching a bit to the test there, but I mean, part of it's also because the analysis is the more interesting part, which is that, the insertion sort is closer to linear time after it's been almost when it's been like pre-sorted like that. And if we use powers of 2 for the gap, then it's O of n squared. But if we use if we basically insertion sort elements that are 31 items apart, and then we do insertion sort on items that are 15 elements apart, then items that are 7 elements apart, then items that are 3 elements apart, followed by items that are 1 element apart. So in other words, if insert sort the entire thing, we can actually show that our big O time is so it's n root n time. So n to the n to the 1.5. That's what that is. So everybody kind of get that basically the way Shellsort works is that we select these like subarrays that are of like, here they're of items that are 3 apart. So we're insertion sorting items that are 3 apart. And then we finally do an insertion sort of the items that are that are 1 apart. So you just build up your gap sequence based on how big the array is, and then if you use this sequence to the k minus 1, then you get this runtime. But other sequences give other performances. Other gaps give other performances, and we don't know what the best gaps are. We can show that we've shown that we can get stuff that is really close to O of n. So n to the 5 over 4, or n to the 7 over 6. But we don't have but that's just doing a practical analysis, right? Saying that like if we run this a bunch of times, this is what it looks like. But we haven't been able to mathematically prove it. Nor have we been able to mathematically prove what the best sequences are. And some of them are really weird. So that one's kind of interesting. Still an open question after decades. Merge sort, though, is not an open question. It has been, it is an old algorithm. Older than us, pretty much. So merge sort is, it's a divide and conquer algorithm, meaning it's going to take n log n time. So it actually works off of 2 hacks, one of which we've already seen. The first hack is that that an array of size 1. So this single item, it's already sorted, right? This item is already sorted. Okay, because it's just anything of size 1 or size 0 is automatically sorted. Hack number 2 is is that there's an operation that we've done before called merge. Okay, and merge basically says that if you've got, you know, two sorted arrays. So here I've got 1, 3, 4, and 2, 5, 6. Then it takes only linear time to merge them together. And merging them together is fairly quick. In other words, merging these two sorted lists into one sorted list, right? To do that, well, what I do is I could look at if these are linked lists, I look at the head of each of these linked lists, right? So I'll take this guy and I'll look at the head of this list and compare it versus the head of the list. The smaller one I remove and put it as the head of our output. Then I just repeat. 2 versus 3, which is smaller? 2 is, so it goes next. 3 versus 5, which is smaller? 3 is. 4 versus 5, which is smaller? 4 is. Now at this point, we've got nothing to compare, so we can automatically just drag everything from this end over to here without doing any comparisons. Why? Well, because these were bigger than anything that's been put in here already, so we can just, and this is already in order, so we can just slap them onto the end. So basically we do one comparison for every item, essentially. And the comparisons for leftover items are, is there still items left? So their example is this, right? To merge, look at the first item in both sequences while we're not finished. Compare the two items from two sequences, copy the small current item to the output, right? So let me zoom in here. So, right, you've got 244, 311, and 478, and 324, 415, 499, and 505. So you look at the smaller one. Which one of these guys is smaller? 244 is smaller, so it goes in first. 244 is smaller than 324, so it goes in first. 311 is smaller than 324, so it goes in next. Then 324 gets compared to 478. 324 is smaller. 415 is smaller. 478 is smaller than 499, right? Everybody see how this works where we just look, we're moving one item at a time, right? Not a very difficult algorithm to deal with, right? Everybody got it so far? Okay. So analysis of this is that it takes O of n time. Okay? Where n is the number of items you're trying to merge. The caveat, yes?
Do they have to be, like A and B, do they have to be sorted?
They have to be sorted. They have to be sorted. So merge assumes that the two things you're getting is sorted. Otherwise, it's not going to work. Okay? Requirements. The array cannot be merged in place. So if we're dealing with an array, you can't do it in place. You have to, basically, if you have, if you've got size A and size B, you need a third array that's size A plus size B, right? To put them into. So if you have n items that you need to merge, you need O of n space to do the merging. If you're dealing with arrays. If you're dealing with linked lists, they're just nodes, so you just move them every which way. You just need an additional pointer for the head of the first of your output. Okay, so merge sort actually is really good for linked lists because they don't need any extra space. But regardless of whether you're using linked lists or array lists, the time for this thing is actually going to be the same. The linked lists just happen to be more space efficient here for merge sort. So merge sort ends up being, so the idea behind merge sort is, well, if merging two sorted arrays takes O of n time, then what I'm going to do is I'm going to sort the left half of my array, sort the right half of my array, and then merge those two sorted arrays together into a single array. So merge sort looks something like this. So merge sort is actually kind of looks pretty silly as an algorithm. Okay. And I'm going to make it recursive, and it's going to be recursive because that's the easiest way to write it. So sort, so this is merge sort. So sort some list, right? We'll call it list. Okay, let's call this left is equal to the left half of list, right? Super technical there, right? But it's not that hard as operation. Figure out what the left is. Then right is equal to the, right half of the list, right? Again, not being super technical here. It's pretty easy to figure out how to split these to do what's called a slice operation. You know, slice these in half. Okay. So we've got the left and the right. So then left is, I'll have to put some extra stuff up here on top because remember it's going to be recursive, so I'll have to put in a base case. So left is equal to sort the left side, right? So we're calling the same algorithm. And as you might imagine, right is going to be equal to the result of sorting, okay, the right. And then we return merge left and right. Left and right here are both sorted, right? So we split the list into two lists. We sort the left half, we sort the right half, and we return them merged together. Okay? We need a base case. We need a stopping condition. Okay? Sort list if list has 1 or 0 items, right? It doesn't really make sense at that point to split it up at all, right? Right? You can't split one item. You can't split 0 items. And sorting a list that's 1 or 0 items, well, remember, that's instantaneous. All you have to do is just return it because it's a single item, right? So if it has 1 or 0 items, return list. So that's our base case. Base case has 1 or 0 items. Otherwise, split in the left half, split in the right half. Sort the left half, sort the right half, and then merge those two things together. Okay, that looks simple in practice, but how does that work actually? Right, so how does that look like? Yeah, everybody got it down? Okay. How does it look in practice? Let's look at 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so here we've got an array. I chose a power of 2 because I choose powers of 2 because they're easy to split into halves. And of course, once we're done with this, you're going to ask, well, what happens if we don't have a power of 2? I mean, and the general idea is we make do as best we can. But anyway, so first thing we need to do is we need to split this into a left half and a right half. Okay, done. Okay, split into left half and right half. And then we need to sort the left half, and then we're going to sort the right half. So we'll just work on sorting the left half first. Okay? And then once those two sides are sorted, we merge them together. So now we're just going to focus on sorting the left half. To sort the left half, and let me switch this into 6 and 2. Otherwise, otherwise it's not going to look too exciting here. 6 and 2, 1 and 7, right? We split this left half into a left half and a right half, and then we need to sort the left half, right? Okay, so we're going to sort the left half. So to sort the left half, we have to split it into 2 halves. Sort the left half, sort the right half. Okay, well, 6 is already sorted because it's by itself, and 2 is already sorted because it's by itself, right? Okay, so now these 2 items have been sorted, so they need to be merged together. So let's go ahead and merge these 2 items together. This pair of items gets merged, these singles get merged into a pair. So we compare which goes in first, 6 or 2. 2 goes in first, then 6. Okay, so we sorted the left half of the left half, and we got to sort the right half of the left half. Okay, so to do that, we split it up into halves, which instantly return themselves because guess what? They're done. They're single items. So now we merge 1 and 7 together. Okay, 1 and 7 get merged into, well, 1 goes in first, so then 7, right? And so now we can finish sorting the left half of this by merging these 2 sorted lists together. Okay? 2 and 6 and 1 and 7. So 1 is smaller than 1 is smaller than 2, 2 is smaller than 7, 6 is smaller than 7, so we add 7 into the end. Everybody see how that was just the merge operation we did over there? Okay, now we added the right half, which, again, we just split this in half, and then we end up splitting this in half, and we see that these are just single items, and then we merge them together into 3 and 5. Then we merge 4 and 8 together into 4 and 8. Sorry, again, I sound worse than I actually feel. So, all right, so then we need to merge these pairs together into a quad. So 3 and 5 get merged together. So 3 is less than 4. 4 is less than 5. 5 is less than 8. And then 8 goes in last. And then we merge, and then so we've successfully sorted the left half, we've successfully sorted the right half. Now we got to merge the left half and right half together. Okay. 1 is less than 2. 1 is less than 3. 2 is less than 3. 3 is less than 6. 4 is less than 6. 5 is less than 6. So now we have 6, 7, and 8. 6 is less than 8. 7 is less than 8. And then 8 is less than left, so we copy it over. And so now the table's sorted. So now it's sorted. So how long did that take us? Well, we've got 3 layers of merge. Really, the splitting doesn't take any time at all, right? Splitting it up doesn't really take any time at all. You just kind of say, grab these items, whatever, right? What takes the time is the merge, which is O of n time. If you've got n items, it's going to take O of n time. So if we look at these like layers, right? The first layer, we're merging, if we're switching between like combining these. The first layer, we're merging 8 singles into 4 pairs, right? We're merging 8 items together, so that takes 8 steps. Then we're merging 4 pairs. Again, 8 items, so that takes 8 steps. Then we're merging 2 quads, which takes 8 steps. So 8 steps, 8 steps, 8 steps. Each of these merge items took O of n. Each of these merge steps took O of n time. Okay, so this took O of n. This took O of n. This took O of n. So the question is, if I generalize this, how many O of n's will there be? Say we had 16 items, right? If we had 16 items, we'd have, in addition, you can imagine that if we had 16 items, I'd have another one for the numbers 9 through 16 over here, right? That would have their own, which would have had their own singles, their own pairs, their own quads, and produce their own octuplet, I guess. Okay, right? So there would have been another 8, another 8, another 8. And then for those items and these items, we would have had to merge them together too, down here with another set, right? So it would have been 16, 16, so it would have been 4 16s. So what's the relationship between 8 and 3 and 16 and 4? Okay, and if we have another thing like this, right, there will be, if we have yet another layer, because we have 32 items, we'll have 32 items and 5 layers. So what's the relation? Yep.
So 2 to the
yeah.
3 or 4.
Yeah. So it's if you have O of n items, then you'll have log n layer. Then you'll have log base 2n layers. So so that's why I said this algorithm is n log n. You have n layers, right? And each layer takes, so you have log n layers, each of which is a merge operation. And each of those merge operations takes O of n time. So you have O of n merge, O of n merge, O of n merge, right? You're merging 8 items. They just happen to be, you're merging a bunch of small things and then a bunch of slightly bigger things and then a bunch of bigger things. But all told, you're doing O of n merges together. It's a nice graphical example of this. So this is n log n time. This is what we call a divide and conquer algorithm, because we keep dividing this thing into half and then working on each half and then combining them. Let's look at another example from the slides. So here we've got another array of size 8 split up into, we split them in half, split those halves into halves. So 50 and 60, they split up and then they merge back together. 45 and 30 get split up into single items. Those single items are sorted, so we merge them back together, 30 and 45. 50 and 60, 30 and 45. Merge those together, right? 30 will go in first, then 45, then 50, then 60. So we've sorted the left half of the array. Now we need to sort the right half. That gets split into 90 and 20 and 80 and 15. 90 and 20 get split up into 90 and 20. They merge back together to become 20 and 90. 80 and 15 get split up. They merge back together in 15 and 18. Then we merge those together to get 15, 20, 80, and 90. And then how does this work now? We do 15, then 20. 15, then 20. Then 35, then 30, then 45, then 50, then 60, and then the remaining two items get tacked onto the end. So it takes O of n time to do. O of n log n time to do this. So I'm going to skip over heap sort, but I'm going to come back to it just simply because if we're going to be dealing with, since I've introduced one recursive algorithm, I might as well go into the other recursive algorithm. Heap sort is not recursive; it requires a heap. Quicksort is the other recursive algorithm, and it's the only one that has really a weird time to remember. Yes.
So you say what happens if you add another one to the that's not true?
Sorry. So what if I add another one?
So how do you do it? Which ones do you start sorting? Because there's not going to be even.
Oh, if you don't have it even, then you're just gonna have to create a rule which side gets more or less, right? So let's assume that the left side ends up with less, right? So if you've got an odd number, so an odd number of items are always going to split up like this. You split it up into an even set and then an odd set, okay? So an even set you don't have to worry about. So the odd set, again, that's going to get split into an even set and an odd set. And eventually you're just going to get to the point where it's split up into something that has 2 on one and one on the end. That one on the end is going to be sorted and then it's going to get merged with the 2. But once you hit that level, but we had 8 items, right? That had 3 layers. Once you introduce that 9th item, we're going to go into 4 layers. There's just no getting around it. So Quicksort. Again, another ancient algorithm. Still kind of the de facto standard. I think it's only recently been replaced by TimSort. Quicksort is very straightforward though. It's very easy to understand, even for a merge sort isn't necessarily easy for the layperson to understand how to do it with like paper and stuff. But Quicksort, on the other hand, is very easy to understand how to do. However, it's easy. It comes at a price, which is that on average it's n log n. Worst case scenario though, it's O of n squared. Merge sort is going to work the same way no matter what, like selection sort. It's going to do n log n, best case, worst case, average case. Quicksort has worst case scenario O of n squared because of, as you'll see, this pivot item. If we have complete trash luck with our pivot item, then we're going to end up with O of n squared time. But if we have good luck, then we have something that runs as fast as merge sort, and we can do it in place with an array. So first, we're going to just look at it like it's magic, right? Before we figure out how to do it in place, and then we'll figure out how to do it in place, because the in place is the part where we're going to test you on the exam. And by the exam, I mean the final. So what we do is that we grab a value called a pivot. So say that we say we basically, you're a TA again, okay? Say I'm using the TA example again. Say you're a TA and you're trying to sort all the exams alphabetically, okay? And you know that selection sort takes forever to do, right? So we'll need a better sorting algorithm. And merge sort seems like it'd take up a lot of physical space to do that. So you try this one, which is Quicksort. So that way that works is that you grab one of these one of the papers out randomly from the pile. Eventually we're gonna move away from random and just say it's the top item. You grab the top item out of the pile, right, and you look at it. The last name is Lars. Okay, so you you just toss it in the middle. Okay, and now you make 2 additional piles, one to the left and one to the right. To the left goes everything that comes alphabetically before Lars, and to the right pile goes everything alphabetically that comes after Lars. Okay. So you don't bother trying to sort it at all besides that. You just say everything left of everything that comes alphabetically before Lars goes to the left, everything after Lars goes to the right. Then you repeat for your left and right piles. Recursively repeat this process until it's all sorted. Remember, you can stop once. You end up with a pile that's 0 or 1. So, but ideally, if your pivot is chosen correctly, if your pivot is chosen, you'll end up with something like in the middle of the alphabet, or the median item at least, right? Because names aren't necessarily distributed evenly. So about half the stuff will go to the left and half the stuff will go to the right. Okay? And then we just repeat this process until it's completely sorted. Okay, so let's look at that with an example on the board. So we call this random item. We choose the pivot. Okay? One, two, three, four, five, 6, 8. Okay. So the idea here is that I am choosing, is that I have these items. I have, I have 5, 2, 7, 1, 3, 4, 6, 8. I want to sort this array. So what I'm going to do is I'm going to select the first item of my array as my pivot. Okay? This is my pivot. Why am I selecting the first item? Because doing anything other than that is kind of hard, and it's always easy to find the first item. Okay? And then I go through the array. Everything that's less than will go to the left. So 2 goes to the left of 5. 7, because it's bigger, will go to the right. 1 goes to the left, left. 3 goes to the left. 4 goes to the left. 6 goes to the right, and 8 goes to the right. Okay? And now, we've got 5 here, we've got these guys, and then we've got these guys. Now we just recurse. So choose the first item as the pivot. Everything that's less than the pivot goes to the left. Everything that's greater than the pivot goes to the right. Okay? So then we recurse. Sort the left half, sort the right half. We've got one item, so it's sorted. Right half, choose the first item as the pivot. Everything less than goes this way. Everything greater than goes this way. This one is bigger, so it goes to the right. So, and then we're done sorting the left half, right? We read just right to left, ignore the vertical spacing, and just look right to left with the circled items. We've got 1, 2, 3, 4, 5. So now we choose 7 as the pivot of the right half. 6 goes to the left. 7 goes to the right. Sorry, 6 goes to the left. 8 goes to the right. And they're single items, so it's all sorted. And we're essentially 3 layers deep plus the 4, which brought us to a 4th layer. Essentially, this is n log n. Each of these, remember, each layer takes O of n time. It took O of n time to decide to put each item to the left or the right, and then O of n time to decide whether to put each item to the left or the right. Only each layer we go down, we choose one. We have to decide for one less item, right? Because we automatically just choose that item as the pivot. Okay. Now, mind you, though, this doesn't look like it's in place at all, right? Another example, right? We would arbitrarily take 44 as the pivot item, and what we'll want is to split. Essentially, we'll want. This isn't how it's going to work, but it's a useful illusion for the next 5 minutes. What we want is basically we want to put it in the middle and partition the elements. Put all the elements that are less than 44 to the left, all the elements that are greater than 44 to the right. Right, that's what we want. And then we want to recursively do this. Okay. So Quicksort's actually a very simple algorithm. It doesn't take too many lines. The Quicksort part of it doesn't. The partitioning part of it is the hard part, right? The splitting it up into left and right. But this is the algorithm. Because we're doing this in place on subarrays, first and last are the first part of the the first index of the subarray, and last is the last index of the subarray. And piv index is the index of the pivot. So the algorithm is fairly simple. It's just this: if the first item's index is less than the last index item, in other words, they haven't first and last they haven't swapped yet, right? They haven't crossed each other's path yet, then you're still operating on a valid subarray. So you'll want to take that subarray, first through last, and partition the elements so that the pivot ends up in the middle, and then you've got a left half and a right half, where the left half is smaller and the right half is bigger than the pivot. And then quicksort the left half and quicksort the right half. That's it. There's your base case, by the way. Just making sure that the index it's valid. So here's the analysis, though. So again, we're doing the analysis before we figure out how this works, which is kind of weird. So the idea here is that basically, if the pivot value is just a randomly selected item, then if we just are going off statistics, right, on average, right, then half the items will be smaller than the pivot and half the items would be bigger. If we did 1,000,000 runs of Quicksort, this is what would happen, right? And so it would split it in half and then split it in half again, and you can only split it in half log n times. So it would take, and each of those splitting in halves would take O of n time. So it'd take O of n, so each splitting is O of n time. You can split it in half log n time, so it's n log n, just like merge sort. However, we are computer scientists. We are programmers. We are information specialists. We do not care about average case. We know that the universe has it out for us. Okay? We know that we are unlucky people. Okay? Things blow up all the time. So we care very much about the worst case. And the worst case scenario is that pivot value is terrible. Okay? Here's an example with our strategy of choosing the first item. 1, 2, 3, 4, 5, 6, 7, 8. Using Quicksort. The best case scenario, the array is already sorted. Right? Well, let's select the first item as our pivot item. Okay, put everything that's smaller to the left. Done. Everything that's bigger to the right. Okay. Okay, now we sort the left, which we're done. Sort the right now. Select 2 as our pivot. Put everything smaller than the pivot to the left. Everything bigger than our pivot to the right. And repeat. Right? That takes forever. In fact, we're sorting one item at a time. So we do 8 on this layer, 7, then 6, then 5, then 4, then 3, then 2, then 1. We can recognize that as we can easily recognize that as O of n squared time, right? That's the O of n squared pattern that we've been looking at in our worst case scenario, if the pivot's terrible. Okay. And on top of it, it would do even worse than in selection sort, because we would also have the overhead of recursion. So we'll figure out how to deal with choosing better pivots later, but for right now, know that that's a spot of bother. Okay. So now, how do we actually do the splitting this thing into left half and right half? Well, if this is a randomly ordered array, it's not really going to matter what everything's order everything's in. So let me go ahead and recreate the array. So I'll use 9 items. So 4, 3. Now I'll use 8 items. So 4, 3, 7, 2, 1, 4, 8, 6. Just to make it slightly different than last time. So we have a couple of variables that we're going to keep track of to do this. The first is that the first index that we're looking at, or the subarray that we're sorting, and the last index. So we've got first and last, right? First and last. Okay? And then this guy's the pivot right over here. Okay, we're going to just, so the first is the index, so I'm going to, so, and I'm going to put this up here. So this is vals index, and these, so anything listed up above the numbers is a pivot, is a value that we're storing. Anything that's listed below is an index. Okay, just to keep that straight. There's only going to be one value that we're keeping track of, which is the pivot. And now to do it in order, right? We selected our pivot value. We just grabbed the first value as our pivot value. Okay. To do this in place, to partition in place, we need two more variables. One called up, and the other called down. Now, paradoxically, right? You'd expect up to be up here and down to be down here, but actually, they're aptly named, because what we're going to do is that up is going to go searching up the array for the first item it can find that's bigger than the pivot. And down is going to search down the array for the first item smaller. So up is going to go up, down is going to go down, up is going to go up looking for the bigger items, down is going to go down looking for the smaller items. Make sense? Okay, so let's see how that works. Because I haven't explained all about the up at all. I just told you what up and down do. So up, what it's going to do is that it's going to look up the array for the first, we're just going to look for the first small, we're going to increment it until we find the first item that's bigger. So 3 is not bigger, but 7 is. So boom, we're going to just stop here. Now we go and look down. We look down the array for the first item that's smaller. So 6 is not smaller, 8 is not smaller than the pivot, 4 is smaller than the pivot. Okay, so now we've gone up till we hit the first item that we found that was bigger, then down until we found the first item that was smaller. Okay? Now that we've done that, what do we do? Well, so long as up and down have not crossed yet, we swap up and down, the values of up and down. So we swap 7 with 4. And actually what happens after this is kind of crazy. So now what do? We just continue. So we look for the first item that's bigger. Up. Sorry. First item that's bigger. Yes.
So, I mean, do we check first before we swap?
Let's check what?
Like if they're bigger.
Well, we swapped them because we found the first item that was bigger and found the first item that was smaller, and we swapped them. So essentially what happens is that the bigger item teleports up to the higher in the array, and the smaller item teleports down. And so now what you're going to see what happens is actually up and down. So we search down for the smaller item. And now that down appears before up, we actually know that we hit a terminating condition. We've actually successfully partitioned this array. And you may be going, well, we don't have, right? I thought we were partitioning it into into smaller stuff smaller than the pivot, and stuff bigger than the pivot. We'll get there, but right now we've got the pivot, the stuff smaller than the pivot, and the stuff bigger than the pivot, all nicely grouped together. If you keep doing the up-down algorithm, and I'll do it on a bigger array to show you, then we're good. So this is what and by the way, this is what you're going to have to do on your final exam. This is one of the questions. This is like a 5-point question. Perform this this partitioning algorithm just for the topmost layer. Don't have to do it recursively, just do it on the topmost layer of Quicksort. Okay, and so I will definitely go over it in more detail. So anyway, now that up has crossed down, we're at a terminating position. So now we need to change it from pivot less than greater than to less than pivot greater than. So how do we do that? It's actually pretty simple. We swap first with down. and then we return down as the index of the pivot. Okay. So now we've got a left half. Now we've got a left half of the array and the right half of the array. So sorting the left half is going to be a bit of a pain because we select 1 as our pivot. So let's see how that works out in practice. First, up, last, down, search for the first item that's bigger, up, first search for the first item that's smaller. Once we get to the end of the array, we don't find anything that's smaller than that, so that's kind of as we should stop, right? So the same rules apply, which is that basically we swap pivot with down, which doesn't do anything, and we return the index of down as our pivot. 1 was our pivot, and then, as you can see, it didn't really sort anything. But let's look at sorting this subarray now, because that's what we'll do. We'll support the left half, which does like this, and then we'll do the right half. So first, last, look for the first item that's bigger, up. Look for the first item that's smaller, down. Last, down. Okay. Found the first item, up and down haven't crossed, so we swap 2 and 4. And then we look for the first item that's bigger, look for the first item that's smaller. Down and up have crossed. So that means we finished doing this partitioning portion over here. So we swap first and down. Oh, and look at that, the left side's complete now. Then we quicksort the left half, we quicksort the right half, and of course they're single items, so they sort themselves out. Now sorting the right half, this would be the first item here, the last item here, and this would also be our pivot. Search up for the first item that's bigger, first item that's smaller. Swap these 2 guys, 6 and 8. Search for the first item that's, again, search for the first item that's bigger, first item that's smaller. And they crossed, so now we know we're done. So 7 swaps with 6. And again, we're done. All right, so again, let's look at this with the bigger array. On a kind of problem you might have on an exam, but with more numbers, right? So let's go with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Okay? So a good number of items here. Right, so 6 in this case, so we've got our first item, our last item, okay? We've got our up and we've got our down, okay? And our first item is our pivot, right? So we're going to be searching for all the stuff that's, so we search up for the first thing that's bigger, down for the first thing that's smaller. So search up for the first thing that's bigger, found it, and search down for the first thing that's smaller. Okay, so now we swap up and down. So we swap 8 and 5. Okay, up and down. And now we continue. Search up for the first thing that's bigger, down for the first thing that's smaller than our pivot. That's 4. So swap the 7 and the 4. Okay, search up for the first thing that's bigger, down for the first thing that's smaller, which is the 1. So swap 9 and 1. Then search up for the first thing that's bigger, down for the first thing that's smaller. They've crossed places, so now we know that we successfully partitioned our array into, you know, stuff that's less than the stuff that's greater than. So now the last step. All right, this was where down was, so now we swap 1 and 6. So now we've got our pivot in between the left half and the right half. And then we would recursively search the this. So 9 isn't too bad of a pivot here. 7 and 8 are pretty good over here. They'll go to the left, and that's fine. But 1 is a terrible pivot over here because 1 is the smallest number, and it's also very lonely. So that's just not going to work for it. And that's going to slow this down slightly, unfortunately. And a lot of times for Quicksort, what you'll see is that once we hit 64 items, again, it'll be paired with insertion sort. So if the subarray you're sorting is less than 64 items, it will just, instead of doing Quicksort, it will do insertion sort because you're guaranteed to be that much quicker. Let's look at the example. Finally, let's look at the example the book has. Selects the first item as the pivot. It colorizes them so that the light purple is bigger than the pivot, and the anything that's smaller than pivot is blue. Okay, so it's colorized them. So now we're going to find the first item that's bigger, find the first item that's smaller, swap them, and repeat. Find the first item that's bigger, find the first item that's smaller, swap them, and repeat. Find the first item that's bigger, find the first item that's smaller. Up and down have crossed, so we know we're done. So now swap the pivot with down. And then recursively apply this. Okay, so how can we solve the problem of not having terrible pivots like that one over there? Right? I mean, ideally, what do we want to do? We loved it if the median of the array or subarray was the pivot every time, because by definition, the median is the middle item. So if we chose that as our pivot, then we'd be guaranteed to have half the things be less than, half the things be greater than. Finding the median I mean, certainly you've been asked to find the average of a list, right? You've been asked to find the average of an array, right? So finding a median can't be that hard, can it? Take about 2 minutes, just a couple seconds if you're watching the video to think about that. And in class, you should be thinking about that and going, wait a second, we've never actually had to find the median of an array. How would you go about doing that? Well, you can think of it like an O of an item and say basic, you can think, okay, for each item, if this, check it against all the other items in the array. If half the items are bigger and half the items are smaller, this is the median, right? But that takes O of n time because you're comparing, O of n squared time because you're comparing each item against every other item. So O of n squared to find a median, so you can get n log n time. Nope, that just brought us back up to O of n squared. So finding the median at least that way, in that naive way, is terrible. Finding the medians actually seems like it might be a hard problem. And honestly, even if we could get it down to linear time, that'd be an annoyance still. But what we're going to do is do something that takes constant time, rather than looking, because we already have a first and a last, so that's 2 items. And it's no trouble at all to find out what the middle item is of the arrays, right? You've got the first item, you've got the middle item. So first item, last item. The middle item is first plus last divided by 2. So if we look at those items and decide to use the median of those 3 items of the pivot as the pivot, then that will speed it up a bit. We'll be guaranteeing that if we have a pivot, if we choose that as the pivot, then at least one item is going to be going to the left, and at least one item is going to be going to the right. So in this case, right, you'd select, we'd sort these guys, and then choose the middle as our pivot item. And to do that, we'd move it to the first location, and then run partition as normal. It's just a small little hack that works out to be slightly more advanced, but it's still, you can because you're just randomly picking values still, you can still end up being unlucky. But Quicksort, on the other hand, Quicksort is a pretty good algorithm, and it's pretty easy to understand. So we'll go over one more sorting algorithm, or these sorting algorithms, and then I'll end the section by going over a sorting algorithm that's not in your textbook, but one I really like to go over, because it's completely different than all these other sorting algorithms. So heat sort, as you might imagine, relies off of using a heap, and we can do it without using any extra space. So, but let's just assume that basically we don't care about space. We have an array and you have a priority queue, right? for each item in the array, add it to the priority queue. Okay? Then, for each item in the while the priority queue is not empty, dequeue the priority queue. That will remove the smallest item from the priority queue, and we would take that item and put it into the front of the array. And then we'd dequeue the next item and put it into the index 1. Take the next item, put it in index 2. And then we'd get a sorted array because we'd be taking all the items from smallest to biggest. It would take we'd have n items to put into the heap, and each item takes log n time. So it would take n log n to put them in, and then to dequeue an item it takes log n time, and we'd be doing that O of n times. So it would take n log n plus n log n, which is O of n log n. So just by putting stuff into a to a priority queue, which is a heap, we can get this, pretty quick, done pretty quickly. But if we are clever about this, if we turn our array into an actual heap, then we don't need any extra storage time. So this is the algorithm I just described. Right? And this uses what we've been doing so far, which is called a mini. What we're going to do, though, to do this in place is use something called a max heap. Now, a max heap is the reverse of a min heap, right? Min heap, the root of each heap is the smallest item in that heap. In the max heap, the root of each heap is the biggest item in that heap. So what we're going to do is that we are going to, so here's what we're going to do. We're going to, for each item, so what we're going to do, if we're given an array and we want to sort it, what we're going to do is that we're going to turn that array into a heap. Now, the way we know how to do, the way I'll describe takes n log n time to do that, but there is an O of n, but the lower bound for turning an array into a heap takes O of n time, and I'll get into that later at the end of this. Okay, but we'll leave how do you turn an array into a heap as an open question for right now. Okay, but once we've turned it into a heap, a max heap, what we're going to do is that we're going to take the top item of the heap and move it to the bottom of the heap. We're going to pretend we're removing an item from the heap, essentially, but instead of deleting it, we swap it with the last item, and then we'll reheapify, ignoring the last item. This makes sense once you actually see it in action. So given an array, we've turned it into a max heap. This is a max heap, right, where every item is bigger than its children. 89 is bigger than 76 and 74. 39 is bigger than 29 and 6. Right, so every item is bigger than its children. And each of its children is a max heap on its own. So how do we sort this? Well, we've got the biggest item at top. So what we do is we take the biggest item and we swap it with the last item in the heap. Okay, in this max heap. Okay, and then we push the last item down. So we swap 6 with the bigger of its two children because it's a max heap as opposed to a min heap. Swap 6 with 74, 6 with 76, 6 with 37, 6 with 26. And then we're done. And then we do the same thing for 76. We replace it with the last item that's, quote, still in the heap. We're considering all the items that we're removing from the front out of the heap. So all the green items are, the items that will be colored green are going to be removed from the heap. So 76 is removed, it swaps with 29. 29 swaps with 74, then 66, and we're done. Then 74 and 28 swap. 28 swaps with 66, then 39, and then it stops because at that point, because those items below it are out, right? We've removed them. So notice what's going on though. We've got 89, then 76, then 74 at the back, right? It's slowly getting sorted by removing the biggest item and moving it to the backmost location. So again, removing 37 over here, swap 37 with 29, sorry, with 32, 37 with 20, right? It's got to get removed. Then 20 needs to get swapped with 32, then with 26. And you just keep continuing doing this until the array is sorted, right? Because remember, the underlying thing is an array, right? What's going on if this is the array, right? Then what we've done is that we removed 89, replaced it with 6, and then reheapified, right? And we've taken the biggest item and moved it to the end. Then we're taking the second biggest item and moving it 1 away from the end. Then the next biggest item and moving it 2 away from the end, and so on and so forth, until the array is completely sorted. So how do you do this in place? Well, the algorithm they give is basically essentially we take the first item, okay, of the heap, and then we consider that a heap. Then we go to the next item, and if it's smaller than its parent, sorry, if it's bigger than its parents, we're going to swap it. And then the next item, if it's bigger than its parents, we're going to swap it, right? We essentially build the heap one item at a time. We look at each item and bubble it up. That's kind of a top-down approach. But the way to do that there's actually an O of M way to do that, which I'll just simply list here for later. Essentially, right, if we build a heap like this where we take the first item, we don't have to push it down at all. Then the next item, we might have to swap it with its parent, and then the next item we add to the heap, we might have to swap it with its parent, okay? And then the next layer, we might have to swap this guy with his parent, and this guy with his parent. Sorry, this guy with his parent, and then swap up again. This guy might have to be swapped twice. This guy might have to bubble up twice. This guy might have to be bubbled up twice. And then each of all these guys on the next layer, they might have to each be bubbled up 3 times. Okay. The other way to go is actually go from the back end. Okay. Well, there's nothing to so if we consider the back end for the half of the numbers, there's nothing to bubble up or bubble down. And then for each of these guys, we actually will bubble these guys down. This guy has only one possible bubbling down to do. Each of these guys has only one bubbling down to do. Each of these guys might have 2 bubbling downs to do, and the root will have only 3 swaps to do. So if you build it in reverse, it ends up being much faster. It ends up being closer to linear time than n log n time to do that. And that's heap sort in a nutshell. Quicksort and merge sort are going to be the focus of the Quicksort primarily is the sorting algorithm that you'll see on your exam, and then merge sort and insertion sort a bit more conceptually. Just know their runtimes and know basically what happens with method calls with that. There is one more sort that I'd like to introduce. There's a table back here, right? And it lists them in number of comparisons, right? You've got selection sort says at absolutely worst in number of comparisons, but if you remember, it does O then exchanges, right? And we care about comparisons versus exchanges because comparisons are cheap, relatively speaking. On the other hand, over here, merge sort and heap sort, they both take n log n time. Merge sort works really well with linked lists. Heap sort works really well with arrays. And quicksort is pretty much good for everything, but you've got the issue that basically you can have the worst case scenario of n log n time. Of O n squared time. But they are all doing something called they're all being measured by comparisons. Now, there is a sorting algorithm we can use, though, that does not do a single comparison, right? All these algorithms use comparisons. So let's look at a sorting algorithm that doesn't really use any comparisons of comparing 2 numbers against another. So we're going to look at radix sort. That's spelled R-A-D-I-X. And it has a very interesting runtime. Radix sort does. Very interesting runtime. And a very interesting space complexity, too. But the runtime is the most interesting part. The runtime is O of Wn. Okay. Where n is the number of items, obviously, but W is the word count. The word size. In other words, for instance, if you're dealing with 10-digit numbers, okay, then your word size is 10. Essentially, it's as big as the thing you're sorting can be. So strings could ostensibly, if you're dealing with like unlimited size strings, then this is the wrong thing for you, because then that W gets very big. But if you're saying that all the words if you're sorting like a bunch of words and they're no more than 25 characters, then in this case W would be 25. Okay, so we'll see why that is for a second. Now this is a very interesting sorting algorithm because it's not going to use any comparisons. What it is going to use is queues. So we're going to do this by sorting some numbers, 3-digit numbers specifically. So 372, 178, 747, 26, 92, 52, 2, 7. Okay, and we're working in the decimal system here. So this means that we need 10 queues, one for each possible value of each digit. So this is the decimal system. Each value has there's 10 possible values, 0 through 9. If these were binary numbers, I'd need only 2 queues, one for 0 and one for 1. I need 10 though, and it's easy to illustrate this. So 0, 1, 2. So we have 1 queue for each number. 4, 5, 6, 7, 8, 9. Okay. So now what we do is that we start by looking at we go through each number and get the least significant digit of each number. Okay? So the least significant digit, the ones place, of 732 is 2. So we're going to take it and put it into the 2 queue. 372 goes into the 2. 178 goes into the 8 queue because it ends with 8. Make sense so far? So where is 747 going to go to? 7 queue. 747. 26 is going to go into what queue? 6 queue. 92 is going to go into the 2 queue. Let me just give me more space because the 2 queue is popular here. So 92. And then 52 is going to go into the 2 queue. And then 2 is going to go into the 2 queue. And then 7 is also going to go into the 7 queue. Okay? So we've successfully put everything into a bunch of queues. So now we go through each queue in order and dequeue them. So 0's completely dequeued, 1's completely dequeued. Now we got dequeued the entire 2 queue. So 372, 92, 52, and 2. Right? It's queues, so they get ejected in the order they got injected. Then 26, 747, then 7, then 178. And that doesn't appear to have done much, but there is an ordering now. What is the ordering? How are things ordered now? By the last digit. So they're ordered by the last digit. Okay, that's interesting. So now we're going to do this again, but instead we're going to use the tens place rather than the ones place. Okay? So 372 needs to go into where? 92 goes into 9. 52 goes into 5. Where's 2 going to go to?
0.
Yep. 2 is going to go into 0 because its 2's place is 10's place is 0, right? 2 we could interpret as 0, 0, 2 because we're dealing with 3-digit numbers. 26 goes into the 2's place. 747 goes into the 4's place. 7 also goes into the 0 queue. And 178 goes into the 7 queue. And now we dequeue. 2, 7, 26, 747, 52, 372, 178, and then 92. Okay, so now if we look at it, everything is now sorted if we only look at the last two digits. So 2, 7, 26, 47, 52, 72, 78, 92. Okay, so now we're going to make a third pass. And obviously what's going to happen is that we're looking at the hundreds place this time. So 2 goes into the 0 cube, 7 goes into the 0 cube, 26 goes into the 0 cube, 747 goes into the 100 into the 7's cube. 52 goes into the 0 cube because it's 0, 5, 2. 372 goes into here. 178 goes into the 1's cube. And then 92 goes into the 0's cube as well. So now we just DQ everything. 2, 7, 26, 52, 98, 178, 372, 747. So this is nice because you don't actually need to do much of your traditional comparing cube. Like you might be going, okay, don't I have to compare like, you know, the number to whatever Q I need to go into? And the answer is not really. Not if you use modulo, because, right, if we're dealing with numbers, I can just simply modulo the last index, and then if this is an array of Qs, I can just simply put it into that appropriate index. Yes? So it's O of Wn, where W is the word size, which is basically the size of this possible. Yes?
It's like strings.
So strings, well, the question is how big are you going to let the strings be, right?
Like small words.
Like if it was 25, or if you limited it to 25, then W in this case would be 25.
Instead of using 9, what would you have?
A to Z. You'd have A to Z if they were all lowercase, or if you were doing uppercase and lowercase, you'd have A to Z and capital A through Z. So that makes it a bit interesting. Right. Now, why am I going into this? Because that seems like a bunch of, it seems like a bunch of overhead. Well, first off, you get the lie and say that it's O of N, even though it's not really. It's O of Wn. And that's not always better. But you don't need a computer to do this sort. You can do it with a machine. Radix sort. So let's look at the Wikipedia page. This is an IBM card sorter that does radix sort on punch cards. No comparisons needed. It just simply looked at them, the appropriate hole punches in the card and put them into the appropriate slots. Okay, so what if we were to implement this on a computer? Well, let's just look at integers. So integers in computers, they are binary integers. So you'd only need 2 Qs, 0 and 1. But how many binary integers, so how many binary digits go into a integer? How many binary digits are in an integer? How many bits, in other words, is an int? It's not 8 bits. 32 bits. There you go. So 32 bits. So that means the word size for an int is 32. So W in this case would be 32. So let's go ahead and just think about that for a second. Let's go ahead and think about that. So so O of Wn would be on our computers would be 32n, and you might like to say that's a constant, but you got to compare that against something like merge sort. So O of n log n. Okay, so the question is that if we've got a log n, which is 32 over here, then how big does n have to be? 2 to the 32th power. So radix sort will be better if you're sorting more than 2 to the 32 items and you don't mind about wasting a lot of, a ton of space because you need queues, right? So radix sort really doesn't compare favorably to this, although it does compare favorably to like doing it via, something like insertion sort, except, insertion sort can be done in place and this can't be. But this is interesting because because again, there were no comparisons needed, right? So if for some reason if we get transported to a parallel universe where comparisons are expensive, then this is pretty cool. Also, if you're just trying to build a machine that does sorting, this is much easier way to build it than to try to, you don't need to compare two numbers, which is one of the big things that computers do, right? Computers do essentially, the CPU essentially does two functions. It adds two numbers together or it compares two numbers and then gives you a result accordingly. That's all. See, that's pretty much all CPUs do. Mind you, they've got much more interesting functions, but at that core, that's what they do. All right, so let's go ahead and take a small break. We are done with chapter 8. So so when we come back in 10 minutes, we'll go on to graphs for the last portion of this.